Hi and Assalamualaikum. Our group members are Sharifah Aina Hazrin binti Said Hassan, Nik Fadliana binti Fauzi Kamarul, Amira Sofia binti Amiruddin, and Muhammad Harith Hakimi bin Hanafi. We are proudly presenting our project, Civil Engineering Materials Sustainable Product for subject ECS 246. We will touch on the introduction, methods, findings, discussions, conclusions, and references. Let's start with our introduction. In this project of ECS 246 Civil Engineering Materials, students are required to do a research on future sustainable concrete or brick for potential application in civil engineering field, based on studies carried out by researchers around the world. For further information, sustainable concrete and bricks are defined as a product that uses less energy in its production, also known as green products, which is environmentally friendly. The basic design that can be classified as sustainable products includes using recycled materials, extending product life, as well as reducing toxic materials. In this research, we will be explained further regarding this concern.
In the journal Concrete Durable but also Sustainable by Professor Dr. I.R. Charles F. Hendricks, the topic that being questioned by him is the sustainability of durable concrete from recycled aggregates. He mentioned that even though the process of concrete leads to unlimited quality of sustainability, it could just be a presumption. The goal of this study is the important aspects such as environmental loading and health aspect should be taken for a closer look.
Channel 2, the experiment from the general properties of concrete with recycled aggregates, influence of properties of the aggregates and their interpretation by Mbara was carried out to evaluate the physical and mechanical characteristic of coarse recycled aggregate grade from actual conventional concrete. The coarse recycled aggregate interface was analyzed with an impact on the characteristic of fresh concrete. The impact of various brick content was also investigated in the recycled concrete. The objective for the experiment was to see the effect on the strength and elasticity modulus of the new material by the strength of the recycled aggregate and to identify the design that determined the quantity of cement required to satisfy the mechanical parameters.
The first article are in regards of concrete with recycled concrete aggregate that was conducted by R. Dillman from University of Essen, Germany. The tests were carried out to assess the effect of employing recycled aggregates form of mature concrete of varying strength on the characteristic of fresh concrete, as well as the effect of adding crushed concrete sand. This written article demonstrated that the strength of mature concrete has no influence on the strength of recycled aggregates or the characteristics of fresh and hardened concrete.
So for the fourth journal, in the journal Recycled Concrete Aggregate, an alternative concept by Dr. Adam G. Johnston, Mr. Andrew R. Dawson, and Dr. Gareth J. Brown state that the manufacturing of the aggregate for concrete product is the most effective and environmentally friendly use of the concrete waste. However, there are issues with the preserving the consistency and the quality of crushed concrete waste because the crushed concrete waste instead of fresh concrete result in product with reduced strength, slump, and workability. The recovery of clean unbound coarse aggregate performed through stage size reduction using communication machine such as standard crushers and grinders is an alternative approach for the recycling and reuse of concrete waste. The goal of the study is to provide the result of 12-month test program of laboratory-based experiment based on this concept. So for the next segment is the methodology.
The methodology used in this journal is the researcher conducted a research based on the comparison between Dutch CUR organization, RILEM and CENTC 154 aggregates on the use of recycled aggregates in producing cement. The pros of using this method is, it is much easier for the researcher because it will only involve a lot of reading without having to do a physical research. But the cons is that there will be no test conducted to prove either the data provided in the earliest research is still eligible to use in the current situation. Next.
The methodology for this journal is the researcher conducted the research based on the influence of recycled aggregates on the properties of new concrete. The coarse aggregate was added to a paste or mortar and then they will be observed in which the aggregate will be initially mixed with water in certain time. The advantages for this method is much easier to analyze different situation and quantity the properties related with water, cement for effective water content in paste. But the disadvantages for this method is the result for quantity of cement is not very accurate.
For this purpose, two crushed and sieved aggregates made of concretes with a compressive strength in the lower 20 Newton per millimeter squared and upper 55 Newton per millimeter squared ranges were used, as well as crushed and sieved aggregate, which will be referred to as the practice mix. The practice mix was taken from the concrete stockpile of recycling site. Firstly, the aggregates tests were done to ascertain the characteristics of the three aggregates supplied. Next, concretes were made. In an oven, the aggregates were dried. The recycled aggregates were pre-mixed 30 minutes before the concrete production based on the quantity of water absorbed in 30 minutes and the amount of individual grading, so that the recycled aggregates were saturated on the surface yet dry. Following that, 110 dm squared batches of concrete were made. Following the addition of water, the concrete mixed for 60 seconds and the consistency was assessed. When the concrete was still considered fresh, the degree of compatibility and flow were measured immediately after mixing, as well as 15, 30, 60, and 90 minutes later. Temperature, air content, and bulk density were also measured. The specimens were compacted and then coated with damp and PE foil. They were demolded and cured underwater for about 24 hours. The compressive strength of concrete was tested on 3 cubes aged 2, 7, and 28 days, as well as the static elastic modulus on 3 concrete cylinders aged 28 days. The tensile splitting strength on 3 cubes aged 28 days, and the depth of water penetration under pressure on 3 slabs aged 28 to 35 days. Frost resistance, shrinkage, and carbonation was also tested.
So in the fourth journal, the assessment and observation of the volume and rate of aggregate released by traditional crushing and dry grinding were part of the investigation into aggregate liberation process. Complete specimen were crushed into a double toggle Stuyvesant jaw crusher and a Stuyvesant smooth rolls crusher as a part of the crushing experiment. The liberated aggregate in each size fraction was weighed to determine the particle size distribution of the crushed product using round efficient test sieves. Visual classification and hand sorting were used to determine the amount of released aggregate. All crushed product size fraction bigger than 6.7 mm were recombined in the dry milling trials, and a representative sample was placed in a rotating mill under settings that promote abrasion of the sand binder component from the aggregate particles. The liberation characteristics were determined in the way stated above. Based on the current differences in the mill operating factors such as charge weight, mill speed, and resident duration, the need for dry product for the preparation of specimen for the binder rehydration investigation is to restrict the use of wet milling method. The pros for the method is the concrete aggregate will achieve its pure composition in order to ensure get the highest quality. So for the next segment is the findings.
The first finding from this journal is the type of recycled aggregates, which is one of the most important criteria on recycled aggregates. There are 3 important types, which are known as Type 1, Type 2, and Type 3. Type 1 is to originate primarily from masonry rubble. Type 2 is to originate from concrete rubble. Meanwhile, Type 3 consists of a blend of maximum 20% of recycled aggregates and minimum 80% of natural aggregates. The requirements for each types are summarized in Table 1. From this table, we can clearly see that the requirement is totally different for recycled aggregates to be classified according to its type. For example, from the table, it shows that the minimum requirement for dry particle density for Type 1 is only at 1500 kg per meter cube, but 2000 kg per meter cube and 2400 kg per meter cube for Type 2 and Type 3 respectively. The maximum content for Type 1 aggregates is intended to be 10%, but an example of 50% of masonry and 50% of concrete mixture may be used for blending natural aggregate. These categories may equate to an increased level of performance. The properties of concrete with recycled aggregates may differ from concrete with only natural aggregates. Rylam had concluded the property variation within concrete up to 20% of recycled aggregates or up to 10% of recycled masonry aggregates are negligible. Second finding will be the properties of concrete with recycled aggregates based on the data provided by Dutch CUR organization, Rylam and CENTC 154 aggregates. The first properties is water demand. Recycled concrete aggregates, notably recycled masonry aggregate, typically have a higher porosity than natural aggregates. Because of this, concrete with recycled aggregates absorbs a higher amount of moisture than ordinary concrete. However, by pre-wetting the aggregate or by partly saturating the aggregate in the concrete mixture, prior to the addition of cement, a concrete will result with properties similar to those of ordinary concrete mix. The next property is workability. High level of aggregate replacement costs less workability. Adding water may increase the workability, but it is strictly advised against because of the adverse influence, the strength and durability of concrete. Basically, addition of super plasticizer will be more sufficient. Alternatively, the amount of water and cement can also be increased simultaneously in order to keep the water-cement ratio to a constant value. The third properties is shrinkage, creep, and modulus of elasticity. Due to the moisture absorption in recycled masonry aggregates, it may display lower shrinkage in the initial stages of hydration. In case of total replacement of recycled masonry, shrinkage may be about 40% higher, which will increase the creep by 15 to 40% and a decrease of 10 to 30% of modulus of elasticity. The next properties is compressive and tensile strength. A full replacement lowers the compressive strength by 20%, but if the fraction is larger than 4 mm, the decrease may be limited to only 10%. The tensile strength marginally less compared to concrete with natural aggregates. However, recycled masonry causing the bending tensile strength to be about 50 to 60% from ordinary concrete. Next, frost resistance. If no extremely high moisture load, concrete with recycled aggregates can be taken as frost-proof. In case of high moisture load, the application of recycled masonry should be avoided for outdoor application. The ability for water and chloride that can penetrate deeper in concrete with such aggregates can cause frost damage. And the last properties discussed is the cost. Extra procedure for the manufacturing of good quality concrete with recycled aggregates will cause the concrete to be in high level or at least equal to ordinary concrete. The third finding for this journal is that either the recycling is possible at material level or construction element level. It is explained that the possibilities for recycling aggregates are considered at material level. In the life cycle assessment, concrete with recycled concrete aggregates consume higher energy for manufacturing, especially for the crushing and the additional cleaning operation. In case of higher percentage of recycled aggregates, the cement requisite will increase to compensate for the potential loss of strength. More water or additives should be added coincides with the increase of the raw materials. In the production of recycled aggregates, there is a larger waste residue than natural aggregates. The environmental advantage of the recycling process at material level only limited to the landscape deterioration and prevention of landfilling demolition waste.
For the journal 2, the finding that I obtained from this journal first is the properties of original concrete, HO. The slump used for this experiment is 40 mm. This table shows the comparing recycled concrete aggregates to standard aggregates. The researchers discovered no significant change between it, with the exception of porosity characteristic. The amount of water that the aggregate will absorb in the mixture is determined by the porosity of the recycled aggregates and the water content in the mixture. Table 2 is show the properties of coarse aggregate. Table 3 lists the concrete that were chosen for conventional and recycled concrete. In Table 4, the mixed proposition used are given, and the result of mechanical properties test is in Table 5. In this experiment, the properties of the recycled concretes were compressive strength, modulus of elasticity, and density and porosity. The compressive strength is calculated using 10 cm cube specimen according to BS 1881.1169. According to UNE 8301, the modulus of elasticity is measured in cylindrical specimen 15 cm times 30 cm. The density and porosity of prismatic specimen were determined 7.6 times 7.6 and times 25.4 cm. This is the mixed design diagram. For the sake of comparison, the mixed design chart for conventional concrete are created with data from HP, HN, and HR, which consider the same as for recycled concrete. The 6 concrete listed have all been produced using the same process and all have the same functioning. This table 6 is cement content for a given strength. For recycled concrete for case 1, to achieve 45 MPa, we need 7.2% extra cement. For case 2, we need 17.3% extra cement to achieve 57.5 MPa.
Now, for the findings of the third journal, first is the aggregate test. The percentage of asphalt granulate in the practice mix far exceeded the threshold value. Second, there is far too high a percentage of asphalt granule was contained in the aggregate made of recycled concrete. The third is the frost resistance of recycled aggregates did not, with one exception, meet the requirements. And lastly, the settleable matter did not meet the requirements. Next, for the test on fresh concrete, the degree of compatibility of fresh concrete compared to the reference concrete increased when run gravel was replaced by crushed concrete. Figure 1 explains the strength values of recycled aggregates and run gravel. Next, the test on hardened concrete. From Table 1, you can see the strength values of hardened concrete M1. And Table 2 is the strength values of hardened concrete M2. Now, from Figure 2, you can see the density of hardened concrete in relation to compressive strength, and Figure 3 explains the elastic moduli in relation to compressive strength. Figure 2 and Figure 3 shows that there is a linear relationship between the density of hardened concrete and its compressive strength, as well as between its compressive strength and elastic modulus. Reduced compressive strength and elastic modulus can thus be attributed to the aggregate's lower bulk density and strength. Compared to the reference concrete, concrete with recycled aggregates has an elastic modulus which is roughly 20% lower. This lower elastic modulus is approximately the same size as concrete with limestone aggregates. Concrete with recycled aggregates and a water-cement ratio that has 0.6 was not water permeable and was resistant to chemical attack. Concrete with the water-cement ratio of 0.5 was resistant to severe chemical attack. The findings on tests on fresh concretes on the whole tensile splitting strength of concrete with recycled aggregates is much higher than that of the reference concrete. As you can see below, the Figure 4 explains the shrinkage of the M1 concrete with recycled aggregates made of mature concrete, and Figure 5 interprets the shrinkage of M2 concrete with recycled aggregates made of mature concrete. We examine 2 types of concrete which are comparable to the concrete examined in this research project, and also determine the depth of carbonation after 1 year resulting from different methods of curing. From Figure 6, it explains the carbonation of M1 concrete, and Figure 7, it explains the carbonation of M2 concrete. According to the depth of carbonation of all tested concretes with recycled aggregates is within the normal range. Lastly, in the frost thaw test, using the CF method, one must distinguish between 2 damage mechanisms. First is the internal damage expressed via the drop in the level of the dynamic elastic modulus in relation to the frost thaw cycles. A 60% drop is admissible. Next is the surface damage expressed as a loss of mass of the test area. The loss of mass and the dynamic elastic moduli as a result of the freeze thaw cycles are shown in Table 6 and 7. This shows that all the concrete types tested with recycled aggregates and an amount of crushed concrete sand.
Okay, so for the Journal 4, as you can see here, for the Table 1, is the total production of construction aggregates in 1996 was some 228 million tons of cement, which about 30% was used for concrete manufacture. And for the Table 2, it showed that the concrete specimen with predetermined mixed proportion were cast in 150 mm³ and allowed to cure in a constant temperature above at 28 Celsius for a period of 28 days. So as you can see here, the Table 2 showed the concrete specimen data for all the aggregate. So in the next Table 3, the concrete mix contains single graded 20 mm and 10 mm siliceous or gravel and igneous aggregate and type M sand. All the grading with grading limit according to BS 882, the particle size distribution of the aggregate were determined by sieving techniques, as you can see at the Table 3. So for the Table 4, show the samples of concrete waste that used in the experiment. We use the reinforced beam sections fabricated with concrete containing siliceous and calcareous aggregate were obtained from Marshall Flooring Ltd of Overingham, Nottinghamshire. The specification for the concrete in the samples are presented in table 4. So for the next one is clean aggregate that released by crushing. There are 4 types of product that were classified. The first is aggregate particles free of binder and sand. The second one is aggregate particles with binder and sand attached to their surface. The third one is aggregations of binder and sand. And the fourth one is fines material with size smaller than 3.35. So for the next one, as seen as figure 1, the proportion of clean aggregate in the size range of product from all the roll crushing stage were higher than the jaw crusher, as the total mass of the aggregate in the concrete specimen was known, assuming uniform dispersion of the aggregate. It was possible to estimate the proportion of clean aggregate which were liberated. And you can see for the figure 1, the set of the crusher was slightly above and below maximum size of single size 20mm aggregate used to prepare the concrete specimen, a comparison of the particle size. So the next one is the visual inspection of the release aggregate indicated that little fracturing of the release aggregate had occurred during the crushing process. Further experimentation demonstrated that reduction of crusher set significantly below the maximum size of the aggregate. Okay, so you can see the table 5 show the liberation of clean aggregate by crushing. So for the next one is concrete that containing calcareous aggregate. The investigation indicate that liberation through crushing was not an effective method of reclaiming clean calcareous aggregate from concrete waste, but the jaw crushing of a concrete waste sample M1 at sets of 15.5mm and 10.3mm result in liberation values of only 3 and 6% respectively. Dry milling failed to abrade the sand binder component from this aggregate. The concrete containing igneous aggregate. Liberation values obtained by crushing concrete containing igneous aggregate appear to be inferior for those concrete containing siliceous aggregate. These lower values are illustrated in figure 2. In the table 7, show a comparison of the particle size distribution of the release aggregate with a particle size distribution of the aggregate which has contained within specimen 120. It is evident that the crushing of the concrete at set of 15mm resulted in breakage and the size reduction of the aggregate itself. So the next one is the concrete containing mixture of 2 single size aggregate. The grading curve of concrete containing mixture of 2 single size aggregate tend to be a bimodal. This is illustrated on figure 3, which compares the grading curve for the single size aggregate in specimen S20 and 120 for those for the experiment mixture of 2 single size aggregate contained in specimen. The mixed proportion for this specimen can be found on the table 2. Alright, so in figure 4, it will show the clean aggregate released by jaw crushing from specimen S20, 10, and the figure 5 is show the clean aggregate released by jaw crushing from specimen 120 and 10. Aggregate liberation studies with concrete specimen contain 2 single size aggregate require size reduction in stage. For specimen S20 and 10 and 120 and 10, this involve a jaw crushing at a set of 22.4mm and size analysis of the product. So for next one is combining the size fraction greater than 10mm size, and the next one is combining all the size fraction greater than 5mm in the size and jaw crushing at set of 10mm. So the table 8 show the revelation of clean aggregate by jaw crushing. As the total mass of the aggregate in the specimen was known, it was again possible to determine the overall proportion of clean aggregate which could be liberated by jaw crushing with set of 22.4mm, 15mm, and 10mm. So the relationship between the crusher set, liberation, and gradient of the liberated clean aggregate from the specimen may be seen from the table 9 and 10. So for the clean aggregate released by dry milling, the level of liberation of clean siliceous aggregate can be increased without incurring significant aggregate breakage or size reduction by crushing the concrete at a set appropriate to the maximum size of the aggregate, and then milling the crushed product. The size reduction produced by the milling action was most marked in the final fraction, but increased the level of release of clean aggregate through the abrasion of the binder sand material that adhere to particles of aggregate in the larger size fraction. The particle size distribution of the clean release aggregate was similar to that of the aggregate in the concrete specimen as shown on table 11. The total mass of the aggregate in the concrete specimen was known, and it was possible to estimate the proportion of clean aggregate which were liberated through the crushing followed by milling. So as you can see here, this is the table 11 that show the grading of aggregate released from specimen S20R through crushing and milling. And the figure 6 show the clean aggregate released from specimen S20R. In table 12, liberation of clean aggregate from specimen S20R. So the communication device is roll crusher set of 18.5mm and milling that which have 30 minutes, 60 minutes, and 120 minutes. So the liberation percentage can see in the table 12. It is noted that liberation value slightly in excess of 100% are due to the sampling of the product, which was used to obtain a representative portion from the crushed material for a milling test. So for the next segment is the discussion.
From the first journal, the sustainable construction in concrete is highly desirable for further research in this matter. It is also requiring the possibility of flexibility and adaptability in construction. In order to reach this level of recycling, a change should take place in conceptual thinking from the waste management, which during the demolition, to chain management during the design stage. The designer has to deal with the design for production, which requires a few waste production as possible during life cycle assessment. Design for environment by using products whose environmental load as small as possible. Design for recycling in a way that superfluous materials are recyclable to highest degree, and the design for the end of life scenario of a building, which appropriate products and an optimized connection between those products has to be selected. Therefore, a balance between environmental profit and a life cycle cost, also known as eco-efficiency, has to be found. Other than that, product reuse requires the product to be as undamaged as possible, which require a careful way of disassembling. In disassembling, there are three types of connection must be known, which are fixed connection, which use either glue, cement, solder, and even clicking, and the parts can be damaged by the connection. Half fixed, which the connection may be disconnected, but some part will definitely be damaged, and non-fixed, which is easy to disconnect and does not damage the part and can be reused. The quality of product that have to be reused in another building must have guaranteed quality. Even though the quality may be not as good as a new product, certain specifications still needs to be met. Next, in material recycling, it involves fewer demands in comparison with product use. The two connections, fixed and half-fixed, between material may cause pollution of the material and disturb the recycling process. In general, the damage of the product is less important because the materials are being recycled anyway. Next, the quality of the material is determined by the effect of pollution or by the impact of aging process. In reusing recycled concrete aggregates for new concrete, it may potentially deteriorate the concrete quality. For example, in steel recycling, it affected less by the impact of pollution because most of the pollution will be removed in the recycling process adopted, which in this case, it will be painting of the steel. Next, quality of the recycled material, as some materials may be recycled over and over without significant quality loss. In some cases, 100% of recycled material is reused in the new material. Overall, the studies have addressed the research question, which in this case, it can be said that there are limitations in quality of the sustainability in concrete. The result that had been stated by the researcher in the study is accurate for the time being because the result will eventually change depending on the further research made by another researcher. The results in this journal is very convincing as it was made in comparison from three other researchers, which are the Dutch CUR organization, RILEM, and CENTC 154 aggregates on the use of recycled aggregates in producing cement. All the aspects explained in the journal is pretty much clear, and it will obviously contribute in development of future sustainable product in terms of manufacturing and production of concrete using recycled aggregates.
Discussion for Journal 2. Due to the increased porosity, the mortar of the original concrete causes the water absorption of the recycled aggregate to rise. This increased water absorption creates a large range of change in density compared to traditional aggregate. In concrete manufacturing, density fluctuation leads to variation in the proportion of the mixture and hence in the characteristic of concrete. An indicator term, the effective absorption coefficient, was created to adjust manufacturing technique for concrete produced with this aggregate. This variable refers to the quantity of water absorbed by the added water and allows water and aggregate to be adjusted in the new concrete mixture. Most of the recycled aggregates utilized in the concrete and brick studies fulfill all current scrapping criteria and recommendations. Next, the variability of concrete aggregate characteristic. A special method of mixing as applied in this study must be used that takes into consideration the effect of the concrete characteristic of the aggregate. Apart from that, concrete using recycled aggregate require a greater cement concentration for a given force. The cement content increased by 7.2% for 45 MPa concretes, and the cement percentage for 57.5 MPa concrete increased progressively to 70.3% for the production of greater strength in recycled aggregate concrete. This increased the overall interface characteristic and longevity of the system. Data dispersion of compressive strength data have also been demonstrated to be similar to conventional concrete. Concrete produced with the addition of dry aggregate exhibit less scatter, which indicates that the mixture is homogeneous and higher in quality. This must be checked for various types of cement mix. If conventional concrete is 10% higher than recycled aggregate concrete, the dry and saturated surface dry mass specific gravity. The replacement of recycled concrete by crushed brick reduced the dry and saturated surface dry bulk and appearance because of the more porous of less gravity of the crushed bricks. There is no increase in open porosity in this decline. This can be explained in reality by a differential in the distribution of porosity. The curing mechanism in broken bricks allows additional absorption of cement paste, which isolate numerous vacuums that will otherwise be linked. Concrete with recycled aggregate have elasticity modulus in line with the equation provided by the Japanese Architectural Institute. Lastly, the research addressed the study issue, which in this case may be stated that there are limitations with the amount of cement required to meet the mechanical requirement. The finding for the cement content of the provided strength are not accurate. However, the other result above is very convincing. With the use of recycled aggregate, it is possible to obtain concrete with good quality in terms of strength and durability in the future.
Journal 3 discussed, although there was no major limitations, the research made it known that a plasticizer or a super plasticizer can be used to control the consistency of new concrete. The loss of workability of concrete, including recycled aggregates, is about equivalent to that of the reference concrete. The compressive strength and elastic moduli of recycled aggregate concrete are lower than those of reference concrete. This was ascribed to the aggregate's reduced bulk density and hence their lesser strength. The elastic moduli of concrete, including recycled aggregates, are substantially lower than those of the reference concrete and are generally comparable to those of concrete using limestone aggregates. The decline in compressive strength and elastic modulus can be minimized by increasing the strength of the cement matrix. The tensile splitting strength of recycled aggregates concrete was found to be greater than that of the reference concrete. Only when 100% crushed concrete sand was added did the tensile splitting strength. Concrete with recycled aggregates with a water-cement ratio of 0.6 was water impermeable and resistant to chemical attack. Concrete concrete with water cement ratio of 0.5 was resistant to severe chemical attack. All of the findings and results obtained from the conducted test are convincing enough, although there are several tests that could vary in accuracy, such as all of the findings and results obtained from the conducted test are convincing enough, although there are several tests that could vary in accuracy, such as the determination of the depth of carbonation after 1 year, since the results depends on natural environmental experiment. The study contributed to the development of future sustainable product with the application of concrete below 100% crushed concrete sand are suitable for concrete for interior structure, whereby 50% lower crushed concrete sand are more suitable for concrete for exterior structures, water impermeable concrete, concrete with high resistance to chemical attack, concrete with a high resistance to severe chemical attack, and frost resistant concrete.
The fourth journal, the research were clear that crushing can liberate clean siliceous or igneous aggregate from concrete waste. According to the result of the pilot study, concrete containing siliceous aggregate appeared to have higher levels of liberation than those containing igneous aggregate. With concrete containing calcareous aggregate, the approach does not appear to be effective. Single-stage crushing liberate clean, unbroken siliceous or igneous material if the crusher set meets the aggregate maximum size. The level of liberation can be increased by crushing with a set smaller than the aggregate maximum size, although the result in the breakage and size decrease of the liberated aggregate in an industrial setting. Research is also being conducted to identify the strategies for separating the liberated clean aggregate from the crushed concrete product. The mining investigation have shown a potential way for isolating the liberated aggregate. According to the finding, mining liberates all of the siliceous aggregate from concrete waste, and successful separation can be accomplished simply by screening the mined product at the aggregate size. Dry mining was utilized in these studies to yield fines product whose rehydration strength qualities could be tested if the rehydration qualities are important. Wet communication products like slurry mining and attrition scrubbing, which are substantially faster and more energy efficient and more cost-effective than dry mining, may be an option. As for research, it proved that there are limitations with the quality and strength of the recycled aggregate for the finding. It have very convincing results as stated above. The recycled aggregate have the future application for this method of this research is useful to achieve a good quality concrete aggregate from the concrete waste. By this reason, the strength and the workability of the concrete aggregate can compete with the new materials resources. So for the next segment is the conclusion segment. So in terms of the conclusion, the overall goal of the research was reached, which was to develop an effective approach for determining whether recycled concrete waste can be used in future construction projects. Concrete can be used to build a sustainable substructure. According to the first journal, concerns about raw material, energy emission, waste and inconvenient procedures to reduce the environmental and health load are already in existence. However, by incorporating design for recycling or design for disassembly into the design method, more could be accomplished. For the second journal, the researchers reported that by lowering the cement percentage to a very low level for minor strength requirement, reinforced concrete with normal strength can be made utilizing recycled aggregate. A mixture of cement-soaked recycled aggregate influences the interface, which improves the interface stability and alkali reservation by adding cement. According to the study, dry recycled aggregate create weak interfacial zone due to the absorption of water and cement particles by the aggregate. This stage of production affects the quality of the mortar recycled aggregate interfacial area, and hence the aggregate longevity to create a highly resistant interfacial zone and link them. The transit duration of this combination must be managed. And the conclusion for the third journal is, the aim of the study is found that none of the recycled aggregate grading evaluated satisfied the requirement. For the most part, the concrete with recycled aggregate has lower values than the reference concrete, implying that the mature concrete strength has no bearing on the strength of recycled particles of the features of fresh and hardened concrete. Although it has been established that when concrete is crushed, homogenization of aggregate strength occurs.
In the fourth journal, 3 potential approaches to the creation of waste concrete recycling system designs were identified. Stage size reduction with crushers and screens is the first option for obtaining partial release and separation of clean aggregate. The purpose of dry screening or wet screening and hydrocyclone treatment of crushed fines is to produce products that can be used as sand substitutes. Next is stage size reduction with crushers, followed by dry milling and screening, can achieve 100% liberation and separation of clean aggregate. Reclamation of the mild fines used as a sand substitute or as a self-hardening material. The last one is stage reduction using crushers followed by slurry miling or attrition scrubbing and screening can obtain 100% liberation and separation of clean aggregate. Mild fines processed by wet screening and hydrocyclone treatment to obtain products sustainable as sand substitutes. Even though there are some limits in the research, all of the findings that have their respective aims have their own convincing outcome that indicates the use of recycled waste concrete has a good future application. Many advantages that can be derived from this research. As an example, it can reduce tip pitch and related freight charges, cheaper source of aggregate than newly mined, reduction of landfill space required for concrete debris, using recycled material as gravel reduce the need for gravel mining. Increasingly, high-grade aggregate for road construction is available only at greater distance, increasing the associated economic and environmental cost impacts associated with the longer haulage distance versus using recycled aggregates. These are the references that we use in our journal. Thank you.